Assalamu alaikum class. Today I'm going to talk about electrophysiological methods in the study of language processing. And the book I've taken this from, I'll share with you guys right on the group. So let's begin. This is our first formal lecture on neurolinguistics specifically. Earlier we talked about psycholinguistics, right? Okay, what I'm going to cover in this explanation of what is EEG, ERPs, are and how they work, understand why these methods are uniquely suited to study language, identify, describe the key ERP components, that is N400, P600, LAN, MMN, and others. Critically evaluate ERP experimental designs and their limitations, connect electrophysiological findings to broader questions in neurolinguistics and applied linguistics. Why this matters? As a research in applied language discourse analysis or language acquisition, you will increasingly encounter neurolinguistics evidence in the literature. Yes. And if you come across such evidence, right, you should be able to interpret them. And you can only interpret them if you have some knowledge of ERP and EEG and how these experiments are done, right? Okay. The brain speaks electrically. What is EEG? Language comprehension leaves no direct physical trace. So it's not possible, that somebody is talking to you or you're teaching language and you come to know immediately that, okay, how this is how language is being processed, right? So there is no direct way. We have to use tools, devices, right? Okay, to exactly know how language is being processed. In other words, like you have to actually peek into the brain, right? What is happening there. And even direct peek wouldn't work, right? So you have to use some devices, right, to understand how language is processed. And these days it is pretty much possible because we have technology like EEG, fMRI, and all that, right? Okay. How neurons create electrical signals, a plain explanation. Think of a neuron brain cell as a tiny battery that charges and discharges. Here is the process in simple steps. Neuron receives a chemical message from its neighbors and its receiving branches, dendrites. Okay, dendrites, you can, look at the picture and the book Language in Mind to understand what are dendrites, right? Because I don't want to get into that we covered in that chapter right from language and mind. So you already know that actually these are the connectors. The message changes the electrical charge inside the neuron, either nudging it toward firing the excitatory signals away from firing the inhibitory signals. So nudging to the firing means that they push the message across, right? And sometimes they do not push the message across, and when they don't, and they are like firing away, so that means this is an inhibitory signal, right? Now, once again, for that, you please look up chapter. I think it's Language in Mind from the book, right? And you read about what is uh, excite, excitatory signal and what is inhibitory signal, right? If you don't understand, in language, it's like pushing. When you're firing, you're pushing, the message, right? So that means when you are away from firing, that means you calm down. These tiny changes produce a weak electrical field that spreads outward from the neuron and like ripples from a stone in water. One neuron's ripple is far too small to detect through the skull. Now, this is something very important. That means कि अगर one a neuron you just simply judge, right? Examine, right? Then this acuity is very small and cannot be detected through EEG or through any other, probably tool. But when tens of thousands of neurons do this simultaneously and are all pointing in the same direction, their ripples combine into wave large enough to measure on the skull. So that means on the skull. So that means like but the waves, which if you have ever gone through the process of EEG, right? So you see the reports that it's the waves, that findings are shown through the waves or interpreted through the waves, right? These waves are the results of collected communication by neurons, right? Okay, it's not that one neuron is communicating, right? Now, here is some key jargons which are usually used here. First one is electroencephalogram, a non-invasive recordings of the brain electricity activity made by placing sensors on the scalp. And if you are not aware of that EEG thing, you can look at the images there, right? You can Google the images, right? So these are actually electrodes put on your head, right, to see the brain activity. Neurons brain cell होते हैं. The brain contains roughly 86 billion neurons that communicate by sending electrical and chemical signals to each other. Electrical potential, the force that drives electrically charged particles to move from one place to another. So there is, there got to be the force, something push, right? Okay, those charged particles to move. When neurons processes a signal, its electrical potential changes. EEG detects these changes, right? Okay, so that means the power of, pushing electrically charged particle actually is measured this way. Now, excitatory postsynaptic potential makes the neuron more likely to fire, and inhibitory postsynaptic potential makes it less likely to fire. Now, when we talk about synaptic or synaptic, right? Please, for that you need to again go to the uh, chapter language in mind, okay, and where the brain structure has been explained and all that, and you learn about what is synaptic and post synaptic potential and post synaptic potential, inhibitory and excitatory. Excitatory means that there's a lot of activity going on. Inhibitory means that activity is very less. The brain is calmed down, right? Open field an arrangement where neurons all point in the same direction. The electrical signals add together and can be detected at the scalp. The cortex naturally provides this because they all are in one direction. As I told you, that neurons' isolated activity cannot be detected. Their collective activity can be detected, right? तो आपको ये बात भी समझनी है. Now, practical matters, because brain signals are extremely small, they must be amplified before analysis, but amplification also picks up unwanted signals. Muscle movements, eye blinks, and heartbeat, these are called artifacts, and managing them is central challenge in ERP research, right? So unwanted signals, can also show some sort of amplification, right? So now the problem is that how do you know that brain has been amplified by these things, okay, or actually some other unwanted stimulus, right? So this is the tricky thing which is to be managed. Another important concept is the reference electrode. Electrical potential is always comparison between 2 points. It cannot be measured in isolation, just as you cannot measure height without specifying about what. The reference electrode is a second sensor placed at a relatively quiet site, typically the earlobe and the mastoid bone behind the ear. Now, you need to understand that. Electrodes are put across, onto your head, right, scalp, and one electrode is to be put, okay, on the earlobe or mastoid bone behind the ear, right? Why? Because here the electricity or electrical activity is very less and it's a quiet site. Now, from the quiet site, right, from the, you know, the peak side, wherever in the scalp, right, okay, you actually try to measure the activity, right? So it's always relative. You need to compare, one point, right, with another point. So all other points in the scalp, right? And the activity in those points in the scalp is actually measured against or compared against air lobes and all that, right? Okay, then we have EEG to ERP extracting the language signal. Now here comes the real deal. The raw EEG signal is continuous stream of electrical activity, large rhythmic waves produced by everything the brain is doing simultaneously: attention, memory, breathing, everyday daydreaming. The background activity is vastly larger than the tiny signals produced by processing one word, right? So that means these activities, do not produce large signals with relation to when the brain is processing a word. Now that is the main point here. So that means we need to measure that difference, right? So let's suppose if the intensity of producing, electricity or electrical charges when somebody is daydreaming or breathing, right, is minimum. Only then, when we process the, a word or any other stimulus, a visual or something like that, right? Okay, which requires a larger, larger activity, right? Okay, or electricity, right? Only then we can see, right, how brain is responding to the language processing and all that. So that's something which makes it possible. Now, how we are going to do that? That's very critical. If you want to isolate the brain specific response to a word you presented, you face a serious signal to noise problem, right? Because there are other signals also available, right? So how are we going to do that? The solution is beautifully simple mathematical techniques averaging. Now, how do we take average? Now, let's have a look at that. Instead of presenting a stimulus once and trying to find the signals in one noisy recording, we present the same type of stimulus many times, typically 25 to 60 repetition per condition. Now, there are two things which you really need to understand here. Number one, what is condition? When language processing is being, judged, right? So there can be two conditions. One condition is that you're given, or that the participants are shown, right, something simple they're already aware of, right? A simple word. Another condition could be an unfamiliar, complex word, right, is shown, and then you can compare, like, the difference in the brain activity, right? Do you understand that? So there, in experimental researches, there are always, conditions, multiple conditions, or at least two conditions, which actually show the difference, right? So here I'm just giving you the example of conditions in linguistic or language processing and all that. And so here is why this works. The two kinds of electrical activity in the recording. The brain responds to the word. This is consistent. Every time you see semantically unexpected word, your brain produces roughly the same N400 response at roughly the same time, and it lines up at the same point in every epoch. Now, epoch means, or means, like, uh, that means it's not just one word, right? There are episodes of different words appearing, right? So one word is processed, right, and measured. That is one epoch or epoch. Then another, then another, then another, and then you actually calculate the average of all those approaches. So, and it also said that multiple as numbers of, trials required for that. But those trials can be done in one go. One go means, like, you're going to put electrodes once, right? And then you're going to, uh, send, the word is processed, then another word, then another word, then another word. But each word, right, processing cycle is, you can say, is one epoch or epoch. Okay. Background noise, this is a random noise of muscles, heartbeat, random neural, doesn't care about your word. It occurs at different time, different sizes, different direction, sometimes positive, sometimes negative across time. Now you need to note down this thing. The N400, always the same time, lines up at the same point in every epoch, right? Now here the waves are different, right? So this is how you learn that, okay, this is noise and this is the language impact, or language, the stimulus related to language, right? This is the impacts of that stimulus, right? Okay, so when you average 40, 50 epochs or epochs, the consistent brain's response adds up and gets stronger. The random noise being in opposite direction at different times cancel itself out mathematically, and what remains is clean, interpretable signal. So, of course, if anything is going in different direction, that you cancel out, right? And only those, waves which are occurring at the same time in the same directions are counted up and you take the average. And this is how it is done. Okay, here is the detail of what I've already talked about. You can read it. Now here, visual illustration, right? The figure below shows what the looks like in practice. Each individual trial is messy and hard to interpret, but when the three trials are averaged together and 400 dp around 400 ms, right, becomes clearly visible because it occurs consistently at the same time in every trial, while the noise cancels out, right? So you can see here trial one, this is trial two, and you can see it's always 400 ms, right? It's all 400 ms, and we can, when we take average, we learn that okay, this is n 400, and the noise is cancelled out this way. Okay, each epoch is a short window of EEG time locked to one stimulus. A typical epoch looks like this. It starts 100 milliseconds before the word appears, right? So that means like when you simply waiting for the word, your brain is active, right? So it starts with minus 100 milliseconds. Here, this should be, there should be negative sign here, right? Okay. Okay, and before the word appears, and then pre-stimulus period is called the baseline, right? So you haven't seen any word, you're waiting for it. That is pre-stimulus period, and that is called baseline. And from there, we actually measure everything. It continues for 800 to 1000 milliseconds after the word appears, right? And this is the response window where ERP components unfold. The epoch ends before the next stimulus. So next word comes, right? Okay, before that, you end the epoch, the first episode, the first trial, right? Okay. So the baseline 100 meters before the word is a crucial reference point. At the point the participant has not yet seen the word. So the electricity activity there is just background noise, not a response. The researcher calculated the average voltage in this baseline windows and subtract it from every point in the epoch, and this sets the pre-stimulus period to 0, right? So this is also a very, very important point. So you can see over here. This is negative baseline. Minus 100. Word appears at 0 ms, right? And then you can see that it goes after 0, it starts becoming, all the milliseconds are positive, right? Is that clear now? So what exactly they're telling you, that this is the baseline. Now you can see over here, the word pair in general brain spot related to what the brain was doing just before, not artifacts or electrode placement. Now 100 ms is the reference point. Participant has not yet seen the word, and the electricity activity there is just background noise. So there is electric activity here, but that's background noise. It's not as a result of a stimulus, language stimulus or linguistic stimulus, right? Now, researchers calculate average voltage in this baseline. So whatever average voltage, right, is there, right? And subtract it from point in the epoch. So the point in the epoch means where it starts, and it starts from, for example, from here, right? Now, epoch starts when the stimulus appears, right? Just from that point, what do they do? That they subtract it, and that's why it becomes 0 basically, right? So they cut it off, right? And after that, like you can see that and this subtraction is called baselining, right? For example, um, you can see that over here, because this is minus 100 milliseconds, right? Okay. And from here, right, if you start measuring the voltage, whatever the electricity activity is there, right, and you subtract it, right, okay, from when the very first word appears, right? So when you subtract it, so it becomes zero. In other words, you just simply discard, those baseline activities, right? Okay, is that clear? And then once you have discarded that baseline activity, right? So that means it's starting from zero. It's an entirely new thing, right? It is just a beginning because you have already discarded the activity. Now, this zero doesn't mean that on EEG it would appear zero, right? This zero means that we are going to subtract any sort of activity, right, before the word appears. That's why it indicates zero. Otherwise, it's minus 100 and onwards. It's still 800 positive. So it's from negative to positive. So this you have to keep in mind. But how do you read ERP graph? This is very, very important thing. Time runs left to right. The word appears at time zero. Everything to the left is before the word, and everything to the right is the brain's response. We can see here, right? Left is subtracted, and here after zero, it's the brain response and all that, right? Voltage is on the vertical axis. By convention in ERP research, negative values are plotted upward and positive values downward. Now, this you really need to understand that. Usually, it comes to mind that anything negative should be downward and anything positive should be upward, but it's other way around when it comes to ERP conventions, right? The baseline period before the word is flat at zero because of baselining, or we have already subtracted that. Components are the consistent peaks, dips you see after the word. They are named by polarity. If it's negative, that is N. If it's positive, that is P. And approximately timing in milliseconds, for example, 400 and 400 means that it is 400 ms after the word. Okay. Now, these are some basic, jargons you need to understand. I've already talked about them, but still, if you want, you can go through. I'm going to send you the lecture document as well. Designing a good ERP study. ERPs are exquisitely a sensitive instrument, which means they pick up everything, including things you don't intend to measure. Good design requires controlling for many variables, and we discussed how controls, previously also. Right? Okay, if I taught you research anyway, and in fact, yes, when we were doing SFL, so I engaged you at least in research, and we talked about experimental researches and all that. Word frequency, length, and participate must be matched across conditions, right? Concreteness, whether a word refers to something physical, neighborhood density, how many other words look or sound similar, often have larger effects on brain responses than frequency alone. Sentence position matters. ERP to sentence initial words look different from ERPs to sentence final word. Repetition of stimulus reduces ERP amplitudes, right? So these are to be controlled. These things are to be controlled when you are engaged in any sort of experimental research because they are confounding variables basically. Eye movement and blinks create large artifacts, especially at frontal electrode sites. So in visual ERP study, words are presented one at a time in the center of the screen to minimize eye movements. So you also need to control that eye movement also. Now, the language-related ERP components, I would like to discuss them. And 400, how we actually interpret that. And 400 is a negative going deflection, peaking at approximately 400 ms after stimulus onset and distributed broadly across the scalp, but largest over the central and parietal regions, the top and the back of them. How it was discovered, Cutis and Hilliard presented participants with sentences like he takes his coffee with milk and sugar, expected ended, versus he takes his coffee with milk and dog, unexpected ending. So they expected to see P300 or component sensitive probability to the unexpected word Instead, they found a large negativity around 400 ms. This was N400, and it launched decades of language neuroscience research. Right, so that's what happened exactly, and you really need to understand that N400 is a kind of, you can say it's not exactly the wave, but the kind of wave with some sort of peak appears that has been named as N400, right? 400 is the time, N is the negative thing, right? Okay, why is this used or what it reflects? N400 is not specifically response to anomaly or error. It reflects the process accessing word meaning from long-term memory. So if you are looking at the word and it peaks, let's suppose N400, right? Okay, dips, and you can see the larger dip or something like that, right? At there's a larger negative dip at 400 ms millisecond, right? Okay, that means your brain is taking more time to process the meaning of that word, right? So that's why it's about the amplitude. If the amplitude is smaller, less brain work. When a word is highly predictable, a word has seen before in the experiment, a word fits naturally onto the into the ongoing discourse and all that. Or if it's larger one, as I told you, the larger a word is semantically unexpected, incongruous, many similar looking neighbors in the mental lexicon, and this activity is a wider semantic network, produces more processing activities. And this is how we distinguish, right? Okay, whether the word is complex or it's being participants are taking more time and all that. Now, N400 has been used to show that second language learners develop implicit sensitive to a word meanings in their new. Now, this is very important. Now, this means that let's suppose if I ask you a meaning about a word and you don't know, right? Now, then I show you that word and I look at your through EEG, the brain activity, right? And I see that N400 dips, and I see that there's a larger, dip. This means your brain is processing, right? One thing, and you perhaps don't know much about that. And let's suppose if I don't see a larger drip, okay, and there is not much, processing involved. Now that means that your brain already knows the meaning somehow, is able to figure out what it means, but you yourself doesn't know it yet. So that means before even you know whether you know the meaning or you don't know the meaning of a certain word, your brain might have secretly, implicitly got the ability to process that, right? So that's why it is important in applied linguistics as well. Okay, close probability, the percentage of native speakers who would complete a sentence fragments with a particular word. High close probability, highly predictable, is smaller and 400. Semantic access, the process of retrieving words meaning from long-term memory. The N400 is thought to directly reflect this process. Orthographic neighborhood, the set words that differ from given word by only one letter. A larger neighborhoods activate more of the semantic network, larger N400. All right, then frontal positivity, the predictions, failures, components. Following N400 in time, there is a positive deflection over the front scarp that appears specifically when a disconfirmed prediction is detected, when the brain expected a particular word but received a different one. And this frontal positivity is an index of predictive processing. The brain had formed a specific expectation, and that expectation was violated. I think I've already talked about all of these things a lot. Now, let's look at the second component, the syntactic repair component. What it looks like, the P600. Now, P means positive. 600 again, ms, millisecond time. Is positive going component typically seen between 500 and 1000 ms, right? It comes between that. After stimulus onset means the beginning. Larger over posterior back scalp sides. Unlike this, it has no fixed peak. Latency, timings, and amplitude vary with the nature of the syntactic difficulty. So, for example, N400, right, peaks at 400 ms, right? Okay, usually, right? So, but here it's not fixed, right? and it depends on the nature of syntactic, but it measures syntactic comprehension, right? This what you have to keep in mind. The P is most commonly associated with syntactic processing, how the brain builds, repairs grammatical structure. It appears when the brain must reanalyze sentence. Initially seemed to have one structure but turned out to have another. Example, garden path sentence, the horse raced past, the barn fell. You likely had to reread this. Brain first reads race, the main verb, then hits fell and has to go back and rebuild the structure. This force reanalysis and triggers the P600. PC600 responses have also been seen to semantic violations involving impossible thematic roles. For breakfast, the axe would only eat toast and jam. Here, the problem is semantic. X can notate, but the brain response resembles the syntactic P600, suggesting that the boundary between syntax and semantics in the brain is not always clean, right? So, yes. So sometimes, because of course, when it comes to syntax, right, it's somehow related to semantics meanings as well. So this shows that. Okay, you can read on your own all of this jargon's explanation because I've already talked about that. Then we have left anterior negativity. The LAN is negative going component appearing roughly 300 500 milliseconds after stimulus onset. The distribution tends to be frontal, sometimes left lateralized, stronger over the left side of the skull. Okay. LAN is one of the most debated component in the field because it appears in the same time window as N400. It can be difficult to separate from N400 in some design. Some researchers argue that it reflects working memory demands involved in holding, matching syntactic information across syntax, rather than syntax processing as such. A related early LAN appearing with the first 200 ms has been linked to very rapid phrase structure building, though others argue it is the general sensory mismatch response, right? So that means this is like morphosyntax thing. The interaction between word structure and the sentence structure agreement means words must match in future features like number, gender, case. The boys run versus the boy runs. MMN, the mismatch negativity, right, is remarkable. It occurs without participants actively attending to the stimulus. In a typical MMN, a participant listens to a series of sound, mostly identical standard sound, with occasional deviant sound differing in pitch duration while doing on an unrelated task like watching a silent movie, a film, without any instruction to attend. The brain still produces a negativity around 150 to 50 ms to the deviant sound. What makes them especially valuable for linguistics is that it responds not just to basic acoustic differences, but to abstract linguistic contrast. Phoneme categories that speakers of a particular language have internalized. This make it a powerful tool for studying phoneme discrimination in infants. The development of language-specific sound categories and implicit phonological knowledge in second language learners. Classic findings at 6 months, infants respond equally to all phonemes contrast regardless of language, but 12 months they show larger MNN processes to construct that are phonologically meaningful in their native language, providing neurological evidence for the beginning of language-specific phonological tuning in the first year of life. So that means that it's only, shows up, or it's a kind of brain activity which we see when the brain is processing uh, distinct phonemes, right? Phonemes which are present in the language and the phonemes which are not present in their language and all that. And it has implications for child language acquisition. A negative ERP component elicited automatically by any detectable change in series of repeated stimuli doesn't require attention and can be measured in sleeping infants. Standard deviation in MMN paradigm, standards are frequently repeated stimuli. Deviants are the occasional different stimuli. The MMN is the brain's automatic change detection response, right? So that means there are deviations possible, right? Uh, Standards are frequently repeated stimuli, right? Deviants are the occasional different stimuli. Now, what does that mean? That, means that when you're repeating the same stimuli again and again and again and again, and one deviant you give, right? So then the standard deviation should be larger, right? Phonemes, the smaller unit of sound that changes word meaning in a given language. You already know about that. You must have studied phonology and phonetics. You can use that knowledge about that. Okay, component used in language production research. ERP research has historically focused on comprehension, but production, speaking, and writing is increasingly studied. Several components are useful here. LRP, lateralized readiness potential, an index of motor response preparation that can reveal which type of information, semantic, phonological, becomes available to the production system first. And 200 associated with the response inhibition, the decision not to respond, useful for examining how the brain suppresses competing word candidates during production. ERN, error relative negativity, a frontal central negativity peaking just after an error or made before the speaker is even consciously aware of that. Now, these all are actually neurological examinations, right? Now, again, like any these components N 400, P 600, MNC, and all that, if I'm not, yeah, that is MMN, sorry, not MNC, right? So like all that, right? These are some other, components, right? Okay, which used in language production research, basically, right? I'm not going to talk about them in detail because here, where our main focus is on comprehension and all that, not the production. But this is also these are also being explored, right? So I won't be discussing all these three LRM, LRP and 200 ERN in detail. But what you really need to understand that these are also some of the components of brain activity, right? Okay, which can be examined through EEG, and they can help us understand language production. Okay, making inference from ERP data. When ERP can tell us aptitude, how large is the response? Larger aptitude generally means more processing efforts. Latency, when does the response peak? Later, latency can indicate slower or more effortful processing. And topography, where across the scalp is the response largest. Different distributions suggest different underlying brain systems are involved, right? So this means that it's about the region also. The most basic inference from ERP difference is that the brain is sensitive to whatever is manipulated. If unexpected words produce a larger N400 than expected word, the brain has detected the difference, and even if the person makes no overt response. Now, this is very important. I mean, this is like cross-checking participants' explicit knowledge about language learning and the uh, you know, uh, implicit behavior of the brain, right? So this is very important. I mean, so that the researchers can check this through this ERP technique and not. Critical concept ERP research is the linking hypothesis, theoretical bridge between a major neural response and the psychological processor you want to study. You cannot directly observe semantic access. You observe electrical patterns, argue based on accumulated evidence that these patterns reflect semantic access. And every ERP inference depends on the quality of this hypothesis, right? So hypotheses are uploaded as new evidence accumulates. What ERP cannot tell us has excellent temporal resolution, millisecond precision, but poor spatial resolution. You cannot determine exactly where in the brain a response originates from the skull's recordings alone. This is why ERP research is often combined with fMRI. So this is the limitation. It doesn't tell you exact location with precision, right? Which location, which part of the brain, right, actually got activated and all that. All right. Now here I have given the summary of all these. Please have a look at that. And I believe that I haven't missed out anything. If you have any question, you can ask me on your WhatsApp group, right? And because I couldn't take the class, right, that's why I thought that I should record and send it to you. And yes, I'm going to send you a task for this week very soon. Thank you. Take care. Allah Hafiz.